the set X defined in that way is compact. We want to show that this set is compact. So we are going to let this be an open cover of X. Let that be an open cover of X. So if that is an open cover of X, then it's a collection of open subsets of X whose union is the whole of X. It's a collection of subsets of X whose union is the whole of X. So if it is a collection of subsets of X whose union is the whole of X, then that means there must exist a set which contains 0. So how are we going to, we want to show that it's compact. That means we have to show that every open cover has a finite subcover. So how are we going to construct that finite subcover? We are going to construct it in such a way that it first covers the 0, then other elements will be covered later on. So if this is an open cover of X, if it's a collection of open subsets of X whose union is the whole of X, then there must exist a set which contains 0. So we have to first cover 0. So what that means is that then there exists an open set W in U which contains the 0 element. So let W be X intersection negative R and K. So by the way, this is a subset of R with the usual topology with the usual topology, then considering that X as a subset of R with the usual topology, then the subspace topology induced by this set, will have a collection of such sets as an open sets. This is what I mean with the usual topology of R. How can we define a subspace topology? If A is a subset of R, then the subspace topology induced by this A is a collection of open sets of this nature. A intersection W, where W is open in R, where W is open in R. So open sets considering the induced topology by A, they are just the intersection of a set A, which set A in this case is X, so that is X intersection an open set in R, intersection an open interval. Open sets in R are just open intervals. So if this is a subcover of X, it's consisting of sets of this nature. Yes. So there exists an open set W which contains the 0 element. So that set looks like this, where R and K are natural numbers. So that is our W. Now, what do we realize about this W? So W contains an infinite number. W contains an infinite number of elements. Of set in X. This set constructed in this way has infinitely many elements of X and elements elements of X not in W are finite. Elements of X not in W are finite. Elements of X not in W, they are finite. So we are going to let them, those elements, let the finite elements be A1, A2, up to AK. Let the finite elements be those ones. Now, what do we realize about those elements? Now, since this is an open cover of X, collection of open subsets of X whose union is the whole of X, so that means there exists elements. There exist sets U1, U2, up to UK in that collection such that A1 is in U1, A2 is in U2, and AK is in UK. Now these sets are not necessarily different. You should take note of that. Distinct. They are not necessarily distinct. Yes, they can be the same. So what have I done there? So at first we covered the zero, then we realized that the set W contains infinitely many elements of X, and the elements of X not in W, they are finite. So since they are finite, then we can get open sets within this collection which contain those elements. Now we have now W, U1, U2 up to UK is a subcover. The subcover of X. Hence, X is compact.